Okay, so we're not going over the problem set, but there is something in the problem set that will come up and be useful. So I'm not going to solve these problems for you because you're supposed to solve them. This one, I think you can do all yourselves. Is this big enough for you guys to see? Should I make it a little bigger in the back? Roger, a little bigger? How's that? One more? That's good? Okay. So so this problem set, this problem doesn't need anything. This problem introduces the word have. So this is a new tactic, which, you have some new fact that you want to add to the list of assumptions. And so the way you do that is you write the word have, you say what that new fact is, you write the list of assumptions, the conclusion, and then why it's true, : by proof. So you'll get a little bit of practice with that in your homework. I just want to point that out. So this is the new tactic that's being added, the have tactic. We're going to use it today, so you'll get a chance to see it before you even need it in your problem set. Okay. Problem 3 teaches you that you can rewrite. We learned about rewriting. You can rewrite at the goal. You can also rewrite at a hypothesis. Okay, so that's another bit of notation that will be useful. Then this one is just more exercises, and this one is about backwards rewriting. So rewriting, if the hypothesis H that you want to rewrite by is x equals y, remember there's not a symmetry in equality. There's a left-hand side and a right-hand side, and when you're rewriting, it's the x that's going to be replaced by y. But if you want to do it the other way around, it's rewrite with a backwards arrow. So this is a left. You type \left, and that's how you rewrite backwards. That'll replace y's by x's, if you want to do that. Okay, that's all I wanted to point out. That's, I think, everything we'll need, and let's do lecture 2. Okay, so the introductions are always not problems, but discussions. So let's read the conversation between Simplicio, our favorite character, Simplicio, and Socrates. Simplicio says, let me explain why I'm doing this. So in the first lecture, I motivated by historical narratives why we want to even be doing real analysis, but we didn't do any concrete math. So let's do some concrete math, and then you'll see where technically there are problems with what we're trying to accomplish. Okay, so Simplicio says, hey, can you tell me about how Newton computed pi? Socrates says, yep, it begins in the year 1666, roughly. Newton's 23. Anything significant about that year? That's Newton's year of miracles, Annus Mirabilis. If I recall, he was forced to leave Cambridge because there was a plague. There was a pandemic, and he had to quarantine at home. So I don't know what you did on your quarantine, but this is what Newton did on his quarantine. And he made all kinds of groundbreaking discoveries on calculus, optics, gravitation, etc. And Socrates says yes. And one of the first things he discovered that year was what we now call Newton's binomial theorem, a new version of the binomial theorem. That's what I want to discuss. Can you tell me about 1 plus x to the n? Do you guys all know the binomial theorem? Yeah. So you take 1 plus x to the n, you multiply it all out, what do you get? And what you get, so Simplicio says, yeah, sure, I know that. You multiply 1 plus x all out, you get n choose 0 plus n choose 1 times x, n choose 2 x squared, because there's just a 1 here. So it's just increasing powers of x's, and then the binomial coefficients, n choose k. All right, so far so good. Everybody's with me. These are the numbers in Pascal's triangle that you can easily read off of the nth row. And yes, it's called Pascal's triangle from the 16th century or something, but it's much, much older and has been discovered in all cultures around the world. Socrates says, excellent. And do you know sigma notation? Does everyone here know sigma notation? Some do, some don't. So let's remember what sigma notation is. Simplicio says, I could have written the same thing as a summation as k goes from 0 to n of n choose k x to the k. So in general, if you have a function from the natural numbers to the reals, and you want to express the summation f of a plus 1, and so on up to f of b, where a and b are, so it's the sum of f of k as k ranges from some integer a up to some other integer b, you write it in summation notation. Summation sigma, k goes from a to b, f of k. Okay, just making sure that that's all set. Very good. So we have that. Would you allow me to write this sum as an infinite sum, going all the way out to infinity, not stopping at n? There's an n here. There's also an n here. This n is actually not necessary. Can you sum all the way out to infinity? What do you think? Why not? Yeah, Jeffrey, or why can you? Okay, that's okay. Wait, don't tell me, don't tell me. Come on. Damon. Exactly. The second k is bigger than n. These binomial coefficients are all zeros. So you're just adding infinitely many zeros to the finite sum. Yeah, no problem. So Simplicia says, okay, I think you see, I think I see what you're getting at. Pascal's triangle has implied zeros everywhere outside of the main triangle. So after here, it's 0, 0, 0 forever, right? So, or put another way, exactly what you said. So n choose k is 0 once k is strictly greater than n. So what? So we've written it as an infinite sum, even though secretly it terminates after finitely many terms. Well, why would you do that? What purpose does that serve? And Socrates says, okay, let me ask you this. Can you think of any way of making sense of this formula when n is not 17, but -1? Can we make sense of this formula that 1 plus x to the n is equal to this summation when n is -1? Damien?
Well, there's a generalization of the factorial, the gamma function.
There is. This was not known to Newton, but that's kind of where we're going. Daniel?
We can like work backwards.
Very good. And what were you going to say? Yeah. Okay. So let's talk about that. So Simplicio says, you can't use binomial coefficients. How do you take three things from -1 things? That makes no sense. Socrates says, okay, sure, but many of the great discoveries in mathematics occur when you realize a way to break the rules. You follow some pattern past its intended limit. Sorry, limit. Put yourself in Newton's shoes. What would he do? And think outside the box. Simplicio says, well, okay, there's another way of writing the binomial coefficient. You can write it as n choose k, which is n factorial over k factorial n minus k factorial. Is this, Roger, this still okay? Should I make it a little bigger? It's okay? You can see? That still doesn't help because what the heck is -1 factorial? That is not answered for another 100 years. But wait, there's another way to write binomial coefficients. We can think about, instead of saying we have n factorial over n minus k factorial, so that's n minus 1, n minus 2, up to n minus k plus 1. And then you can cancel the rest, which is n minus k factorial, cancels on top and bottom, and you're just left with n minus 1, n minus 2, and so on. That's k terms, and then k minus 1, k minus 2 down to 1. So that's still k factorial, but the numerator is now this thing. And maybe with this version of the binomial coefficient, the binomial theorem will still make sense with n equals -1. Let's see. This way we can bypass the issue of dealing with what -1 factorial is supposed to mean and go straight to normal numbers. And Socrates says, can you please write this using product notation? So I'm just trying to make sure everyone knows summation notation, product notation. Sure, it's just like summation notation, but with pi. So this formula that we wrote like this, we can also write at that n choose k. Well, there's this k factorial in the denominator, and then it's a product of n minus l's, like that. Sean. Socrates, whoops, are you sure about the bounds in that product? It's so easy to make a silly mistake when you're doing summation notation or product notation. After writing down the formula, I should have checked to make sure that the bounds, when L equals 1, the first term here is n minus 1. I want the first term to be n. And when L is equal to k, the last term will be n minus k. I want the last term to be n minus k plus 1. Okay, so just idiot check yourselves whenever you write down one of these formulas. What's the last term? What's the first term? I should have said L should go from 0 to k minus 1, not from 1 to k. Okay, is this better? Here it is. All right, fine, whatever. Socrates says, go on. Okay, so if we agree with this pattern, and what is -1? Choose 0. So when k is equal to 0, we have an empty product, and the empty product by definition is 1, and 0 factorial by definition is 1. Right? That's this first term. The n equals 0 term in Pascal's triangle is always 1. In fact, the k equals 0 term is always 1. N choose 0 is always 1, regardless of what n is, including when n is -1, if you follow this formula. Okay, so -1 choose 0 is 1, which makes sense because any row of Pascal's triangle starts with a 1. So even the cth row, whatever c is, c choose 0 is 1. And then let's look at the first term. So we have n divided by 1 factorial. That's -1. Okay, and that makes sense because the cth row of Pascal's triangle, the next term after the 1, it's like the 17th row of Pascal's triangle starts with a 1, then a 17. And then I can't tell you what happens right away. But the next term is always just whichever row it is. So if we're in the -1th row of Pascal's triangle, -1 choose 1 should be -1. Okay? You guys want to take a second to work out the next? I'll give you a chance to work it out in a second. I'll give you some more challenges to work out. What about choose 2? So that's n minus 1 divided by 2 factorial. Okay, there's a 2 factorial on top, 2 factorial on bottom, and 2 minus signs. We get +1. Does that make sense? How about -1 choose 3? n minus 1, n minus 2, all divided by 3 factorial. Well, again, we have a 3 factorial on bottom and on top and 3 minus signs. So that's a -1. Okay, so, okay. Simplicio says, I see the pattern just alternates between plus and -1. So the series is going to go 1 minus x plus x squared, minus x cubed plus x to the 4th, minus x to the 5th, and so on. And that is 1 plus x to the n, where n is -1. Okay, does that formula make any sense? Just because you followed a pattern doesn't mean that that pattern has any reason to actually exist. Right? Does that formula make any sense? How much you test whether it's right or not? Busher says, okay, well, if that series, whatever that is supposed to represent 1 plus x inverse. In other words, 1 over 1 plus x. What does that mean? If I multiply everything by 1 plus x, I should get 1. Okay, so let's try it. So 1 plus x times this infinite series. So I'm going to multiply everything by 1. I'll multiply everything by 1, and then I'll multiply everything by x. So if I multiply everything by 1, that's just the series itself. And if I multiply everything by x, that's x minus x squared plus x cubed minus x to the 4th. Okay, so there's a 1 minus x plus 2x minus 2x, minus 3x plus 3x. Okay, so if I just rearrange the terms, everything cancels out. The only the leading one remains. Great. Everybody's happy with that. Simplicio says, okay, are you allowed to rearrange the terms like that in an infinite series? Simplicio, that's what Socrates says. Simplicio says, why not? What's wrong with that? Okay, never mind for now. You're satisfied that it makes sense to say that the series converges, again, whatever that means, to 1 plus x inverse. Okay. So there's something a little funny. Are we, when there's an infinite sum, you know, we have to sum infinitely many terms, and then we have to sum x. And Simplicio is saying, that's okay, just like regroup them. Can you regroup things? Simplicio says, wait a second, I knew this already. This is a geometric series, right? You guys know how to sum a geometric series. 1 plus lambda squared plus lambda cubed, and so on. You've had, this is like in calc, it's not calc 1, is it calc 2? Or is it in 8th grade or something that you learn what a geometric series? It adds up to 1 over 1 minus lambda. And this is the same thing, except lambda is equal to -x. This will be -x. -x quantity squared is positive x squared. -x quantity cubed is -x cubed. So when lambda is -x, I get 1 over 1 plus x. Great. No problem. Very good. And where might this belong in Pascal's triangle? And Simplicio says, hey, we discovered, here's Pascal's triangle, and there's an extra row. This is the -1th row of Pascal's triangle. And notice it's still the case, like Pascal's triangle is that you sum 1 plus 1 makes 2, 3 plus 3 makes 6. So that there's a 6 here. Right? That was our last exercise, was what is the x squared y squared coefficient in Pascal's triangle was a 6. And 0 plus 1 adds to 1. 1 plus -1 adds to 0. -1 plus 1 is 0. 0. These are all the implied zeros everywhere outside of Pascal's triangle. All right. Socrates says, indeed. And in fact, you can continue this pattern, just keep working backwards. If this is going to be a 0 and that's going to be a 1, this is going to be a -2. -2 plus what makes 1? Three. Okay. So -2 plus 3 makes a 1. And you just continue this pattern backwards and you work out what numbers you need to have so that it's still the sum of two things. 6 and -10 add to -4. And -4 and 10 add to, -20 and 35 add to 15 and so on. Okay. So Socrates says you actually get a whole other Pascal's triangle. This is Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Just with some minus signs above the standard one. So this goes out to all negative numbers. But now they're all infinite sequences. Whereas these sequences, they're still infinite, but they're 0 after a finite number of steps. Whereas these are not. If n is a positive integer, then the product n times n minus 1 times n minus 2 times n minus 3 and so on eventually hits n minus n. And n minus n is 0. And the second you have that, the rest of that's where this becomes 0. So far, so good? Okay. And you see it still follows the usual rule that two numbers above a given number to the left and to the right add to the value below them. Let's try something even crazier, even more exotic. Can you think of a way of making the binomial theorem work when n is a half? Simplicio says, okay, that's really pushing it, but let me see. Here's our formula, right? A half choose k is 1 over k factorial, and then a half minus L as L ranges from 0 to k minus 1. Let's work out the first few terms. A half choose 0, 1, as always. A half choose 1 is a half divided by 1 factorial, which is a half, as always. A half choose 2. Now I have n minus 1. A half minus 1 is negative a half over 2 factorial. So that's a half, and a half. That's 3 2s. That's 8. 2 cubed is 8. And then 1 minus sign, negative an eighth. Take a second and calculate a half choose 3. This is not the quiz, but it's just for fun. Give me a thumbs up when you're done. So it's going to be n minus 1, n minus 2 over 3 factorial. And what does that come out to?
Oh, 16.
Everybody got it? Yeah, you might want to slide over if it's hard to see. Exactly right. A half choose 3 is a half times a half minus 1 is negative a half. Half minus 2 is negative 3 halves. And 3 factorial. So there's a 3 on top, 3 on bottom. And then 2, 2, 2, and another 2 from 3 factorial. 2 minus signs, so it's positive 116. Okay, a half choose 4. Take a minute. What's a half choose 4? You did it already?
It follows the same pattern.
Yeah, it follows the same pattern. A half times negative a half times negative 3 halves times what divided by what? You think it follows a pattern. 1, a half, an eighth, a 16th. What's the pattern? Try it. It's actually not that simple. Yeah, so hang on, Jeffrey. Daniel, you got it? Let's give people a chance to work it out. Sam, did you get it yet? Still working? Give it a second. You think you got it? Okay. Folks are still working. How about Brandon? You get it yet?
The pattern or like the?
The number, the value.
Oh, yeah.
You got it. Sam, you got it?
Yeah.
Okay. I think people got it. So what'd you get? I don't know. Sam. -5 over, let's see. I agree with the 5. So there's a half, negative a half, negative 3 halves, and negative 5 halves. There's a 4, there's a 3, the 3 cancels, the 2 is still there, so there's a 4, a 2, and then 1, 2, 3, 4 more 2s, so that's 2 to the 6, 7. 1, 2, 3, 4, 5, 6, 7, 2 to the 7, 128. Yeah, 6 is 64. Okay. There's not a nice pattern for this, actually. The best way to describe this sequence is this. Because it's going to keep doing weird things where you get this, 7 and 9 and so on. You get only the odds in the numerator, lots of powers of 2, and then the denominator keeps growing by other things. Okay, so it just is what it is, and the first couple of terms of a half, whatever this is supposed to mean, 1 plus x to the 1/2, is just put these coefficients together. 1, a half, negative an eighth. So 1 plus a half x minus an eighth x squared plus a 16th x cubed minus 5 128 x to the 4, and so on. Okay. But wait, this is supposed to be root x. And Socrates says, again, go into Newton's thinking. How would you go about justifying whether this right-hand side has any reason to be equated to the left-hand side? Ayman. Let's square the whole thing and see if what we get is 1 plus x. Exactly right. You guys want to take a minute and do it on your page? Just a little bit. Well, let's start it together and then you'll see. Okay. So Simplicio says exactly this. Okay, I think I see what to do. If we square the formula and multiply everything out, I guess we're supposed to be getting 1 plus x. That would justify calling the series itself the square root of 1 plus x. And Socrates says, go for it. Okay. So I want that whole thing squared. That seems like an annoying thing to work out. That means squaring every term. So we're squaring every individual term and also twice the cross terms. Right? If you, a plus b squared is a squared plus b squared plus 2ab. Twice the cross term. Socrates says, is there a good way of doing this? Is there a good way of keeping track of what's going to happen? And Simplicio says, I know. Let's group things by the power of x involved. Let's work it out by each power. Okay, so what do you get for the coefficient of x to the 0, namely 1? Out of this big sum, whatever it's going to be, how do I get no x's? Just 1 times 1, right? The only way to get no x's is with a 1 times 1. Okay, fine. So that coefficient is 1. How about the coefficient of x? How do I get an x? Daniel?
1 times.
I get a 1 times a half x, and then I get another 1. Well, I get 1 here and 1 there. In other words, I get 2 times 1 times a half x. Right? That's the only way to get an x. So the coefficient of x to the 1, I can't square anything involving x's. I can only multiply the x term by the constant term by the 1, and of course double that. So 2 times 1 times a half x is just x. So the coefficient of x is 1. Okay, so we have a 1 plus an x so far. Let's look at the square term. So how do I get an x squared out of here? Other than Jeffrey, other than Ayman, other than Daniel. Akil. Sorry, Satvik.
Yeah.
Satvik. Akil.
Are we going?
Satvik.
Yeah, so either the cross terms between the two x's
Uh-huh.
or the one times the x squared.
Beautiful. So you get an x squared out of 1/2 x quantity squared. So that's a quarter x squared. You also get 2 of 1 times -1/8 x squared. Okay, so the coefficient of x squared, I get 2 contributions from the constant times the quadratic, 2 times 1 times that. I also get the square of the linear term, which is 1/2 x squared, x to the 4th. So a quarter x squared. So the total coefficient is -1/4 and +1/4. It just cancels out. There is no quadratic. Okay, work out the cubic. How do you get an x cubed term? I mean, you got it already? Yeah, give him a second. Does everybody see how to do the cubic? Who haven't I picked on yet? Joseph, can I pick on you? How do you get a cubic out of this thing?
Cross term from 1/2 x and -8 x squared,
Beautiful. That'll give me an x cubed. What else?
and the cross term from 1 and x cubed term.
Beautiful. And what else?
That's
it. Okay. So the only way to get an x cubed is the constant times the x cubed term and double that, of course. And the linear term times the quadratic term and double that, of course. And that's it. And those two add to 0. Okay. So amazing. If you keep doing this, if you keep checking term by term, all of the other coefficients seem to be coming out to 0. It's it gets, like, what would you have to do to get the quartic term? Akil.
2 times 1 times the x squared.
Yep. Constant times x to the 4th.
Then 2 times 1/2 times the x. So the third term,
Yep. The linear and the cubic
the 1/8 x squared.
and the quadratic squared. And whatever these funny numbers are, they have to be whatever they need to be so that that entire thing sums to 0. Right? Some very bizarre combinatorial thing that's happening. That's being captured by these binomial coefficients, these extended binomial coefficients, Pochhammer sets. Okay, so it really seems like all the higher terms are canceling out perfectly. I bet that if this will keep happening, and we'll just get exactly this 1 plus x. The formula really works. Okay, so Simplicio is convinced. Wait, so now we get a whole other row in Pascal's triangle. Between rows 0 and row 1. Between row 0 and row 1, here's Pascal's triangle. Between row 0 and row 1, there's a 1, a half, -1/8, a 16th, -5, 1/28, I think is the next term, whatever. Okay, in fact, there's a continuum. There's a continuum of Pascal's triangles between the rows of Pascal's triangle, because you could have done this with any number, not just a half. Socrates says, beautiful. And Simplicius says, wait a second. This is all so much simpler than I'm making it. Isn't this the same thing as the Taylor expansion? If I take the function f of x equals square root of 1 plus x, I know how to do this from calculus. You just take the Taylor series expansion, and you get exactly this series that we were looking at. And Socrates says, yes, very good. Unfortunately, Brooke Taylor of Taylor series proved this in 1715, and we're talking about 1666. Okay, so yes, later Newton's binomial theorem becomes subsumed as part of Taylor series, but that's a chronological. Okay, can you think of a easy way to compute a number like the square root of 3 using this expansion? Amen. Plug in x equals 2. Interesting. That's a very, very good idea. Let's think about this formula when x is equal to 2. So we're claiming that this infinite series, I'm going to make a note to self. Simplicio should say, plug in x equals 2. I missed that part of the pedagogical discussion. Yes, absolutely. That is the first thing you should think of, not what actually happens. If you put in x equals 2 into this formula, then you'll certainly get 1 plus 2, the square root, that's square root of 3. Beautiful. What's happening on this side? I get a 1, and I get a half times 2, minus a quarter times 2 squared, plus a 16th times 2 cubed, minus 1 over 528 times 2 to the 4th. The x's are large. And so it seems to me like we'll be adding pretty big numbers if we take large x's. Can we think of a way of getting this formula to work if by making x small? Jeffrey. What's that?
It does not work.
It doesn't work? Okay. You want to think about it for a minute? What could we do with this formula? Joseph.
Oh, if the absolute value of x is less than 1, then the higher order terms would approach 0.
Yes, exactly right. If the absolute value of x is small, then the more powers you take of it, the smaller each contribution gets. Exactly right. So we definitely want to think about making a small value of x, not x equals 2. Okay, I'm glad. I'm glad to see that this is something that isn't immediately obvious. So what does so Socrates says, could you compute root 3 from this? And Simplicio says, yeah, 3 is close to 4. And I know the square root of 4. 4 is a perfect square. So I probably want to be using this identity. Here's the idea. You write root 3 as root 4 minus 1. But really, I know root 4, so let me pull out a 4. And 4 minus 1 is the same thing as 4 times 1 minus a quarter. And that 4 I can pull out and make it a 2. Square root of 1 minus a quarter. Minus a quarter is small. That's where we want to use this formula. Not when x equals 2. The first thing you should think of is exactly right, x equals 2. And then you'll see that you're getting, large, big terms. You're not getting a lot of precision from that. But if you realize that 1 minus a quarter is 3/4, and the square root of 3/4 is root 3 over 2, which means if you double that, you'll get root 3. That's the way to access root 3. Okay, so if I apply our formula with x equals negative a quarter, I guess what I'll get is that root 3 is, well, exactly equal, but I'm going to cut off the series, so that's why I say approximately equal, to 2 times the series, and the series is 1 plus a half x minus an eighth x squared plus a 16th x cubed minus 1 over 5/28 minus 5 over 128 x to the 4th when x is negative a quarter. And if you work that out, just these 5 terms, take just those 5 terms, the fraction comes out to this. First of all, it's just whole numbers. Everything is whole number arithmetic. It's fraction arithmetic. You get this thing, and if you work out what that is, it's 1.732. And the square root of 3 is 1.732. That's really good. If you're in 1666, you don't reach for your TI-82 and check that your answer is pretty close, right? Newton's doing this by hand, working it out, and he sees, hey, that's really good accuracy. I like this formula. I can work out square roots really efficiently by pegging them to square roots that I already know. Okay, Socrates says, great. Now you're seeing the power of Newton's binomial theorem. Okay, so let's go all the way back to the original question. what can Newton say about pi? How would Newton get to pi? Simplicia says, okay, well, what is pi? The definition of pi is its circumference to diameter. The ratio, it's a ratio, it's a unitless quantity. It's the ratio of circumference to diameter in a circle. Where are we supposed to find a length here somewhere? And Socrates says, okay, that's a good first idea, but what did Archimedes teach us? Simplicia says, Archimedes, what does Archimedes have to do with pi? Archimedes has everything to do with pi. The reason pi is important is because of Archimedes. The fact that pi is the ratio of circumference to diameter, so what? It's some arbitrary constant like any other constant in the universe. The fact that it's one constant to rule them all is due to Archimedes. Archimedes is the one who proved that pi is not just the length, it's also an area, it's also a volume, it's also a surface area. Pi arises everywhere. And Archimedes tells us that the area of a unit circle is pi r squared. So when r is equal to 1, the area of a circle of radius r is pi r squared. When r is equal to 1, the area of a unit circle is just exactly pi. So, okay, pi is an area. So what? Where do we see a circle's area lurking somewhere? Satvik.
You like think about it, connect like integrals, integrate under like y equals the square root of 1 minus x.
Beautiful. Exactly right. Simplicia says, wait a second, let's think about, okay, Descartes and Cartesian coordinates says that a circle, you know, there's a geometric object called a circle. There's also an algebrogeometric object, which is, the algebraic object is the variety, or the polynomial equation x squared plus y squared equals 1. And the fact that those two things are the same is thanks to Descartes. So we can make that into a function, because that's by itself, the circle is not a function, right? It doesn't pass the vertical line test. But exactly as Satvik told us, we should think about y equals square root of 1 minus x squared. That's the series we have, except just replace x with a negative x squared. So we know what the expansion of this is. It's 1 plus a half minus an eighth plus a 16th minus 5/28, 5 over 1/28, where x is replaced by negative x squared squared, negative x squared cubed, negative x squared to the fourth. And if you work out what those coefficients are, I'll spare you the arithmetic. 1 minus a half x squared minus an eighth x to the fourth minus the 16th x to the sixth minus 5 over 1/28 x to the eighth and so on. Okay, so that's our expansion of negative of the square root of 1 minus x squared. And exactly as Satvik said, that is the area under the curve. And let's go from, let's say, 0 to 1. Doesn't matter, we can go from minus 1. It's simpler just to go from 0 to 1. So the area under this curve from 0 to 1 will be what? Sean, pi over 4. Pi is the whole circle. This is a quarter circle. This is pi over 4. And over here, we're going to get something that's very, very easy to integrate. Okay, Socrates. Luckily for Newton, he had just invented calculus. So he knows how to integrate these things. How else could he compute this area as an integral? So pi over 4 is the integral from 0 to 1, square root of 1 minus x squared. We know this as a series. Integral from 0 to 1, this thing dx. I'll just integrate them term by term, every single term, one by one. Socrates says, whoa, hang on. Why are you allowed to, you know what, forget it. Never mind, sorry, just keep going. Keep going with your calculation. Splish says, okay, whatever, weirdo. So if we integrate term by term, we get this pi over 4, and I know how to integrate 1, that's just x. The integral of x squared over 2 is x cubed over 6. The antiderivative of x to the fourth over 8 is x to the 5 over 40. I can write these things. I'll evaluate them at 0. That kills everything. I'll evaluate them at 1. That just leaves the fractions. At 1, minus the 6, minus the 40th, and so on. So I get that pi over 4 is, well, exactly equal if we have all the terms, but roughly equal if we just take a couple of the terms, this fraction. How cool is that? So Newton got an infinite series for pi. And if I evaluate just 5 of these terms, just up to the quartic, up to the, these first 5 terms, and I have to multiply everything by 4, this was pi over 4, If I multiply everything by 4, I get this fraction, and that fraction is 3.18. Not 3.14, but 3.18. Not bad, with not so much work. You like that? That's pretty cool. Socrates says, okay, not bad indeed. You know, it's true. What Socrates says is there are a lot of math papers that have basically 0 ideas. There's you just do something that nobody has done before, but you combine things that everybody already knows and nobody bothered to do before, and here's the paper. A really good math paper can have like 1 really genuinely new idea, maybe 2. Newton's already introduced taking the binomial theorem out of the positive integers, in fact, taking them out of the integers altogether, using this alternate version of what choose means, and then working out this calculus. Anyway, we're 5 new ideas, and he's not done yet. He's going to have new idea number 6. He's got an even better way of doing this. Can you think of what it might be? You're quarantined at home, 1666, no Fortnite, no Snapchat. You got nothing to do but stare at this piece of paper and play. Remember when we had that square root of 3? And we tried x equals 2, and that was no good because the terms were getting big. And then we tried x equals -1/4, and that was good because x was small, and we were getting more and more precision from the powers of x. Newton's thinking, we're setting x equals 1. We're getting no further precision from the powers of x. Can't we do something that gets us more cancellation faster, Jeffrey?
You try integrating from like 0 to 1/2, because that's still like a nice angle.
Simplicio says, what's idea number 6? Socrates says, remember how you integrated up to 1 in your series? You have all these high powers of x, but you're wasting them by going up to 1. What if you integrated up to 1/2? Why 1/2? Simplicio says, oh, cool. The series will converge more rapidly, but wait a second, that changes geometry. Instead of a quarter circle, we now have what? We have this weird sector thing. We have this, the area under this curve, up to 1/2. But wait a second, that's not so bad. This is a 30-degree angle. That's 1/12 of a circle. So that's pi over 12. What's left is a triangle with base 1/2 and the 30, 60, 90. I know how to do this. It's √3 is the height and 1/2 is the base. So if we integrate not up to 1, but up to 1/2, we'll get pi over 12 plus √3 over 8. And we'll get to stick 1/2 in for x everywhere and get 1/2 to the 5th and 1/2 to the 7th and 1/2 to the 9th. We'll get much better cancellation this way. We'll get a much closer, maybe, approximation. So if you use just these 5 terms, you get a much more complicated fraction, of course. And if you isolate pi, so I have to subtract √3 over 8, I have to multiply through by 12. So pi is about 12 times negative √3 over 8 plus this fraction. And what you get is 3.14161. And the reason I give you those extra decimals is, remember, pi is 3.14159. So we're off by 2 parts in 100,000. That's 10 to the 5, using 5 terms. And doing this bare hand. Okay, if you're in 1666 and you want to compute pi and you want to do it accurately, you are not drawing a 360gon and measuring the length and working out this. Come on, this is so much cleaner. Okay, you appreciate the ideas that have gone into this work of Newton? Yes, Newton was very impressive indeed. Okay, I left here a Veritasium video that you guys can watch about this story. In fact, the series for pi, very similar to this one, was discovered 2 centuries earlier by an Indian mathematician, Madhava, and it would take 2 more centuries until mathematicians figured out how to justify. Well, what does it mean for a series to converge? For a sum of a bunch of things to converge? What does it even mean for a sequence to converge? You have a whole bunch of numbers. What does it mean for a bunch of numbers to converge? What does it mean for a series to converge? Can you reorder the series? What if the series is actually a function? And it's a function of a variable. What can you say about the limiting function? are you allowed to integrate term by term? Which means what? You have a limit and then you have an integral. The integral is also a limit, right? It's a limit of small rectangles. So you want to interchange those two limits. Can you do that? It's great that we computed all of this, but are you justified by all of these things? That's real analysis. Okay, so last time I just gave you a historical version. Now we have some actual mathematics to dig our teeth into for what real analysis is about. Can we reorder? Can we sum a series? What kinds of functions occur as a result of summing a series that depends on a variable? Okay, make sense? All right, on with some actual real analysis, please. Are we ready for actual real analysis? So, next world. Any questions? Sat.
So, about like the extension of the Pascal's triangle, we saw that like the negative integer rows obeyed like the addition rule.
Yes.
But the continuum of like fractional rows, do they also obey the addition rule? I don't think so, right?
So if you take 1 and 1/2 and you add them, you get 3/2. So there's a 1 here and a 3/2. And what's 3/2 choose 2? 3/2 choose 1 is 3/2. 3/2 choose 2 is 3/2 times 3/2 minus 1, which is 1/2, divided by 2 factorial. So what is that? 3/2 times 1/2 divided by 2, 3/8. And what is 1/2 minus 1/8? 3/8.
Okay.
Right? So it still works, but it just always works with the row with
Okay.
n replaced by n plus 1. Yeah. That's a consequence of this version of the binomial coefficient. Okay. All right. Any other questions? Let's do some actual real analysis. All right, the main definition. This definition is the definition to motivate all other definitions. We're now doing real analysis. The first step to making Newton's arguments rigorous is to spell out exactly what we mean if we have a sequence and it converges. It'll take a bit of work to work up to this definition. Okay? And more importantly, I want to convince you, I don't want to just tell you, here's the definition, let's start working with it. Why? Why would this be the definition? It's a very not immediately obvious thing that this is the right thing to do. And this is how you should work. Let me give a little aside. Probably Euler is to blame for this. I didn't track it down. When we write functions, we write f parenthesis x parenthesis. And then when we write sequences, we write a sub n. A sub 0, a sub 1, a sub 2, and so on. There's no reason. Why do we have these two conventions? It's just historical accident. Okay, so we're going to rectify this. A sequence is nothing more than a function from the naturals to the reals. So we're going to unify these two notations, and we'll write f of x for real valued function. We'll also write a of 0, a of 1, a of 2 for sequences. Okay, just want to throw that out there. So if every other textbook is using this notation for series, for sequences, and then this notation for functions, we're not. We're going to have one notation for both. A sequence is just a function whose domain is the natural numbers. You guys remember the words domain, range, domain, or codomain, or whatever? Okay. Now, the definition that mathematicians eventually came up with for what it means for a sequence to converge was actually so bizarre it was invented twice. It was invented once by Weierstrass in 1860s, and his is the version that took off. But in the 1810s and 20s, right around the time of Cauchy and Fourier, when all this stuff was going on, another guy, Bernard Bolzano, also independently invented this definition. And nobody cared. Nobody read his paper. Nobody thought about it. It's only decades later, after Weierstrass's work was known to everyone and being used by everyone, that they were like, wait, Bolzano did this too, right? You see, it's right. That's the beauty of writing things down. You write things down, you publish papers so that they're there in the literature. And someone long after you're dead can say, wait a second, we got to give this Bolzano guy some credit too. He was there. So Bolzano was developing these exact ideas, but he was too far ahead of his time and the community did not accept his abstract concepts. I say this to say that there's no reason for you to accept blindly what I'm about to do. That's why I want to have an argument about it. Okay? The mathematical world didn't accept it the first time it came out. Took another half century before somebody else came up with it yet again. And then people were ready for it. Okay, So without further ado, here it is. A sequence. A sequence is a function from the naturals to the reals. Could be to other things, but it is real analysis, so I'll say reals. Yes, Brandon.
Yeah, no, so when you say the sequence, like from like natural numbers, are we including zero, I guess?
In this course, this will kill earlier, myself from, I don't know, 10 years ago would say 0 is absolutely not a natural number. We start with 1, 1, 2, 3, 4, 5, and I have matured. And the English way of doing things is 1, 2, 3, 4, 5. The French way of doing things is 0, 1, 2, and there's no way I'm going to let the French have it. The French won't. Okay, 0 is a natural number. It has to be. We will later get to why. The right thing is for 0 to be a natural number. So I say whole numbers when I mean the numbers 1, 2, 3, 4, 5, and natural numbers when I say 0, 1, 2, 3, 4, 5. So as much as it kills me, I have to include 0. I don't want to, but I really do have to. Daniel, you wanted to?
No, I'm always seeing natural numbers 1, 2, 5, and whole numbers 0, 1, 2.
If you like, everyone has their own definition. In this course, there won't be any whole numbers. There will only be natural numbers, and natural numbers, I declare, start with 0. Okay. Given a sequence and a real number L, we will write that the limit of A is equal to L and say that the sequence A converges to L if for every epsilon there exists an n, so that for all little n greater than capital N, we have A of n minus L is less than epsilon. Everybody got it? No, of course not. What the hell is going on here? Okay, so what's going on? Dang.
Like, my eyesight started.
Oh,
Given a sequence, what n dollars?
can I zoom in a little? Does that help?
A.
Yeah, A is the name of the sequence, like A0, A1, A parentheses, A of 0, A of 1, A of 2. That's a sequence, just a bunch of numbers in a row. For every natural number, I give you some real number. And now I have a hypothetical limit. I will write lim A equals n, the limit of A is n, to say that the sequence A converges to L. And what does that mean? It means for every epsilon positive, there exists a natural number n, so that for all little n greater than capital N, A of that little n minus the limit L is less than epsilon. What the hell is going on? Let's take a step back. Here's the, this definition is probably not the first, second, or even 10th thing you might come up with, but over time, over the course of this course, I hope you will see the importance of this way of doing calculus. You'll see that it embodies a beautiful negotiation between precision and effort. So let me try to make that into a little story. I think of a conversation between an engineer's got blueprints, and like a factory worker, mechanist, and a machinist rather. A machinist is working with some big machine in a factory, and the engineer's got a great idea. Okay, so we're gonna make some thing, a widget, whatever. We're gonna make a widget, and its length has to be 1 foot. And I need, in order for this widget to work, I need it to be within a tolerance of 1/100th of an inch. Can you do that for me? And the machinist says, well, yeah, I can do that, but I have this equipment that will make your widget exactly 1 foot in length, give or take a tolerance of 1/100, but I'm going to have to run it for 10 hours or something. What did I say? 10 hours to guarantee that tolerance. There's going to be a cost imposed on your specification of a tolerance. And the engineer says, you know what, I'm sorry, I misread what I was, my own writing. Could you make the tolerance within 1/1000th of an inch? Really, really precise. 1 foot, give or take 1/1000th of an inch. The machinist says, I can do it, but it'll cost you. Now I have to run this thing for 40 hours, not 10. But if you let me run it for at least 40 hours, if you keep letting me run it even farther, it'll be even more precise, but give me at least 40 hours of running the machine, and then I'll be able to get you within 1/1000th of an inch. You envision this scenario? And so as long as this conversation can continue, no matter what tolerance the engineer comes up with, the engineer can't say, make it exactly 1 foot. There's no such thing as exactly 1 foot. It's always within a tolerance. So what's the tolerance that you'll allow me? No matter what tolerance epsilon, as long as it's positive, the engineer comes and asks of the machinist. The machinist will say, okay, this is how many hours I'm going to need. I'm going to need 1,000 hours to run this thing. I'm going to need 1,000,000 hours to run this thing. Whatever that number is, after that amount of time, I will have the tolerance that you asked for. If that can always be achieved, regardless of the tolerance that's being asked for, we will say that the equipment converges in this analogy. So let's read the definition again. Weierstrass's or Bolzano's definition. We have some process that at time n returns a reading, A of n. A of n is the length of the current length of the widget as we're chopping more and more metal off of it or adding bits of metal onto it to make the length what we needed to. Our ultimate goal is to make the length L. We're never going to get exactly L. So if for any tolerance epsilon positive, no matter how small, there will always exist a minimum time n, capital N, so that for any future time, little n, greater than capital N, we are guaranteed to be within that tolerance. The actual reading is within epsilon of the limiting reading. That's what it means for the sequence to converge. And the picture I have in my mind is this. Okay, so here's the width. This is time. And the width is over here. I added some metal. I shaved some off. You know, once we got to 40 hours, now I'm still shaving, I'm still doing stuff, but I'm within my tolerance. So it's a proposition. It's a statement that for any tolerance whatsoever, okay, if you make the tolerance even smaller, I might have to go even farther up. But then at some point, every single future value here will be within that tolerance. Okay. So let's just stare at the definition one more time. Where was it? Right here. A sequence converges to L if for every epsilon, for every amount of tolerance, there exists some amount of time n, so that for any future time, little n greater than that minimum time n, the tolerance is satisfied. That's the definition. Engineering is what saves pure mathematics. Okay. Does that make sense? At least a little bit. We have to practice this a lot before we get really good at it. But that's the key idea. So what makes this definition so powerful is its universality. The machinist is promising, give me whatever the tolerance is. It's not for a fixed tolerance. It's a theorem about all tolerances. Whatever the tolerance is, no matter how stringent, I will always meet it at the cost of potentially using more resources. Here's something else about this definition that's really, really important. We never said, you know, the way Cauchy phrased these things was similar to this, but he said something like, you know, a sequence AN converges to L if as n goes to infinity, AN gets closer and closer to L. What does closer and closer mean? What does goes to infinity mean? Those are wishy-washy words. You can't work with those words. We've removed words like eventually or at infinity and these squirmy words, and we've traded that, the ambiguity of that way of talking, with the precision of there's a cost. Everything, there's no solutions in this world. There's always costs and trade-offs. The trade-off is we have to use universal and existential quantifiers. For all epsilon, there exists an n. That's why I needed you to be good with quantifiers. We're going to be using them all over the place. Okay? There's no more hand-waving about what happens as n gets large. We have a concrete challenge given any tolerance epsilon. Can you find a specific threshold n? And that's the idea that was the key breakthrough that allowed calculus to become real analysis. Okay. How do we write this definition in lean? We write it like this. We're going to call this the limit of a sequence, seq_lim. I don't know. You can call it whatever you want. I called it seq_lim. You notice seq_lim is now one of the new definitions in our video game. Seq_lim, you're given a sequence as a function from natural numbers to the reals. You're given a hypothetical limiting value L. And then what you're defining is a proposition, a true or false statement. Is it true or is it false that A converges to L? How do you determine whether it's true or false? You determine it by determining whether it's true that for all epsilon positive, there exists an n, a natural number n. Let me make this slightly nicer. Maybe like that. That's slightly nicer. I wish I had a better way of controlling where the new line was. Anyway, for all epsilon positive, there exists an n, which is a natural number, so that for all natural numbers little n greater than capital N, you're within the tolerance. Looks just like the usual definition. Okay, this syntax is hopefully familiar from the have tactic that you already know and love for those of you who did the homework. If you haven't done the homework yet, well, you haven't played with the have tactic, and that's okay. We're going to play with it a lot ourselves together. The special symbol def is instead of have, means that we're about to define something. Seq lim is the name of the definition, in this case, the limit of a sequence. You could have called it something else. Our assumptions are that we're given a sequence. These are the inputs to the function. The input is itself a function and a real number L. And then after the colon goes the kind of thing that we're trying to, what the output of the function is. In this case, the output is true or false. Yes, the sequence does go to L, or no, the sequence does not go to L. Okay, so that's a prop. A prop is a proposition. It's something that can be true or false. So seq lim is really a function. Its input is a sequence and a hypothetical limiting value and returns true or false, whether or not the condition is satisfied. After the output comes the definition of the function. Colon equals is how you say, now I'm about to give the thing that the condition. And the exact condition to be tested is for all epsilon, yada, yada. All right, you don't actually need to learn this syntax because you'll never be writing definitions. The big difference is you can add a have inside of a proof. But when you make a definition, it has to be a global definition. It has to go over here. So you would never make a definition inside of a big proof. You can have some new fact inside of a proof, but you won't be defining things. Okay, and notice that seq lim has now been added. And as usual, if you forget what it means, you click on it, and it's got some words there for a sequence and a real number. We say seq lim holds if for all epsilon exists and such at the end. Okay, does that make sense? All right, let's try it out in practice. We have 6 minutes. I think we can do it. Let's try. And of course, we're not getting to the other two worlds that I planned for today. Here's your task. Suppose that your machine is so good that the second you turn it on, it gives you a widget of length L. Every single time. You're just right on the money. No error at all. Okay? So you have a constant sequence. If you have a sequence, you have a function A from the naturals to the reals. You have a real number L. And the assumption is for every value of n, A of n is already equal to L. At least for the constant function, can we prove that the constant function converges to L? That the function that always takes the value n, for every n, always takes the value L, can we prove at least for that? Like the picture we should be thinking about is, here's our window, except it's always L. The dots are all on L. So can we prove that whatever the tolerance is, we'll be able to find, we'll stay within that tolerance. Dang. This is, I'll throw a quiz. I need to throw a quiz in, right? So I'll throw a quiz in a second. I have to teach you some new tactics. One tactic is called change. Change is, you see how the goal says seq lim. And you're like, what the heck is seq lim? Like, what am I supposed to do when I see seq lim in the goal? And what you can do is you can say change what it says there to something equivalent to it. And the definition of seq lim is for all epsilon there exists an n, so that for all n, this thing. So I'm just going to copy this. That's the hint. The hint is to copy these lines and paste it in. Ah, you can't even see it. Okay, so I've pasted in change for all epsilon greater than 0, there exists an n, so that for all n, a n minus L is less than epsilon. And that's your seq lim. When I execute that, all it will do is now the goal has become for all epsilon positive, yada, yada. Okay, here's your quiz. What's the next line? Just the next line. Just the next line. What do you do when you have a for all epsilon bigger than 0, yada, yada? What are you supposed to do with that? Okay, so just put your name on a piece of paper, write what the next line is, tell me what you think it is. This should take about 15 seconds. What do you do when the goal says for all epsilon? What's the tactic that helps you make progress for a universal quantifier? Yeah, you can look back on your previous notes if you forgot which one it is. A question, or you have the answer? a thing at the end. I just want to know what you think the next line is that will make progress when there's a universal quantifier.
You can like do 2 in 1 step.
You could do 2 and 1, yeah. Feel free to do 2 and 1 if you so choose. 1 is enough. Whatever you want. Something that will work for them. What's that? Less of a chance to mess up. Although after the first word, anything you put is okay because it's up to you to name the variables, right? So what's the word? Okay, so the quiz is over. What's the word? Intro. Okay, so I'm going to type intro. Let's say epsilon and maybe a hypothesis on epsilon. Okay, so if you wrote intro, give yourself a point, rip it out and hand it over to maybe Joseph. Can I pick on you since you're centrally located? Okay, pass it over to Joseph. Intro epsilon H epsilon. Okay, let's see if we can do this in 2 minutes. I think we can. So look at what happened after the intro. Now we have a real number epsilon. The engineer has brought in the tolerance and the proof that the tolerance is actually positive. So there exists some n, so that for all n after that, an minus L is less than epsilon. What do you think we should use? Use 1, use 0, use 100, use whatever you want. Use 42. Okay, so now n has turned into 42. So for all little n, at least 42, we have to prove this inequality. What do you do with a for all statement? Intro. Okay, so give me an n and give me the hypothesis on n that n is at least 42. So now I have the n. I told the engineer, really I could do it today, but give me 42 days. And I'm going to hang out. I'm going to go to the beach for 41 days. I'll come in on the last day, turn on the machine, hit it on the dot, and hand it over to you. Okay? So on day 42, you better have it done. So n is at least 42. How do I make progress? Anyone? Yes, let me break it into 2 steps. You're absolutely right that you could do this now in 1 step. I want to know that an is equal to L. I know that for all n, but I want to know it not just for all n, but for this n. So that's called specialize. So let's specialize a const to n. Okay, and now we have an minus L. Okay, and now we have that a of n is equal to L. Now let's rewrite that fact. Rewrite a const. And now we have that L minus L is less than epsilon. That's what we have to prove. That's what we're trying to prove. How can we simplify L minus L? Ring natural form, ring NF. Okay, and now, is it exactly H epsilon? It won't work because we have the absolute values.
Wait, so
What's that?
does it not get rid of it? It's like,
It doesn't get rid of it by itself, but there's a new tactic called norm num, which if you have any numerical value and you want like 3 squared or something, or you want absolute value of 0, it'll evaluate the function on actual numbers. Okay, so if you ask for more help, it'll say try norm num, and ring NF will only do ring operations. Absolute value is not a ring operation. Okay, but norm num will normalize the numbers. Now I have 0 is less than epsilon. The hypothesis is epsilon is greater than 0, and show me more help. In fact, those 2 things are the same. Okay, so how do I? So I do have exactly the same thing here. Exact doesn't exist anymore. Exact is dead to us. The new tactic is called apply. So let's apply H epsilon, and we have solved the goal. Okay, so that's the proof. That's simplicity. Let's just check in. I realize we're a little over time, but let's just check in on what this would have looked like in natural language. Because I want to compare what we write formally to what the natural language proof would be. So the proof in natural language, you would say if a sequence has the same value for every term, then it converges to that constant value. What's the proof? Okay, we have a sequence A of n where A of n is equal to L for all L, and we want to show that this sequence converges. By definition of convergence, that was the change tactic, we need to show that for any tolerance epsilon positive, we can find a point n such that if n is greater than n, then we have the tolerance. Right? That was change. Then, this is almost trivially simple. There's no reason to say that. I had an AI do this, of course. since A of n is equal to L, then A of n minus L is L. That was specialize and rewrite. And L minus L is 0. That was ring. And the absolute value of 0 is 0. That was norm num. Since epsilon is positive, for any positive epsilon, what is the AI doing here? I should have read it before posting it. We can choose any n we want, like 1 or 1,000 or 42, and they would work equally well. Therefore, for any n greater than that value, you have that this thing is equal to 0, which is what we were trying to prove. Okay. Do you see how this is wishy-washy still to me? Like, it is precise. It is it's a proof that would be accepted in any other section of 311, but I like this. Anyway, we'll get some more practice with it. We're out of time. I will convince you. My goal is to convince you that that this middle section is actually a better way to work.